It's a little bit closer. It's a little bit easier to read. There we go. So each one of these guys gets broken into two separate things. There is a smooth version, S1, with a little bar on the top, meaning that this is a smooth representation of the model. And I'm drawing it this way, but we know it actually looks kind of weird here. Here is all the details. And that's represented with a little hat on the top of the model. That's got a little details. Now quickly, because we're going to come back to this, the way we're doing this is we're using a Laplacian operator to get Laplacian coordinates. And again, remind yourself what that is. If I've got a triangular mesh here, and I'm trying to draw this in 3D, draw that up and there, and there's a piece there and there. What we're basically doing is looking at the average of the one-ring neighbors around the vertex on a mesh and saying, you know, if I took the neighbors of this guy and I averaged it out, I'd get a point somewhere along here, sort of on the ground plane of that average. And then if I subtracted the vertex from that average, I get basically a vector. I get a vector that says if I knew my neighbors, I could figure out the average location of those neighbors and then add that vector back into it, and I'd get this guy. And in fact, that is that vector right there, and B, which has got an X, Y, and a Z coordinate because it's actually a vector. It's not an offset along the normal there. It kind of looks that way, but that's an actual vector that says, given the average of your neighbor, the wind ring around this guy, if I add this vector to that neighbor, I can get back to my original coordinate. And so this guy has, in this paper, they put a little doodad on the end of it right there that says that is a Laplacian coordinate. All right. So the cool thing here is that if you have this, if you've got a mesh, you know, some sort of crazy mesh of a face or whatever, and there's a whole bunch of triangles, if you take all these triangles, which are vertices without the apostrophe on the end, without the dash, and there's X, Y, and Z, and you do this conversion where you take these guys and convert it into that. You have a big list of vertices, V0, V1, V2. You do the Laplacian operator on it, and that produces another list of vertices, V0 prime, V1 prime, V2 prime, all the way down. There's a way to go back. There's an L inverse. This is a matrix multiply. We talked about the matrix before. And this is a Poisson solve where you basically invert the matrix, kind of. You can't just invert this matrix because this matrix is uninvertible. But if you stick on just a little bit of extra information onto this matrix, you can solve for this matrix in a least squares sense. And so you can actually do this sort of inverse. And so this inverse is a little bit of a misnomer. When I first read it, I was like, whoa, when I first encountered this, I was like, no, it isn't an inverse. It's a inverse Laplacian operator, which is a little bit more complicated than just inverting the matrix that takes you from here to there. This way you have to do a little bit more work, but it isn't horrible. So that basically means that we can go from a world space representation into a Laplacian coordinates representation, which is just a whole bunch of vectors from the average of your neighbors, and back and forth. We can go back and forth in this thing. And there are a whole bunch of papers, by the way, that are very interesting based on this. The Laplacian operator has been around for a long time, but in computer graphics, it became very popular in the early 2000s. And there's some papers like Surface Mesh Optimization, I think, is a good paper. And these are in the bibliography of our current paper, if you want to look at it. And there's also Surface, oh, I can't remember, there's another Surface,
Surface mesh editing.
Maybe it's mesh editing, and there's a mesh editing and there's a mesh optimization paper. And both of these are very much worth a read. They've got some really cool properties to it. All right, so that's it, okay? So what we've done is we have the source, and we've broken it into S0 smooth version. Gotten rid of all the details, just have the basic. Oh, by the way, inside the paper, and I kind of glossed over this, they create the smooth surfacing, a smooth surface by doing Laplacian filters. And you're like, what? I thought we were doing a Laplacian operator. Well, that exact same operator, you know, that sort of, that representing a mesh by the average of its neighbors. You can use this as a sort of same kind of deal to filter a mesh. You can say, well, if this is the average of the neighbors, I can move this mesh point closer to the average. And I can do this kind of iteratively. It does a very nice job of smoothing out the mesh without changing the geometry of the mesh all that much. So it's kind of cool. It's a neat way of doing things where you're not representing the mesh with Laplacian coordinates. You're just applying that operator to the mesh to smooth out the details. So we break the source into the smooth version of the mesh, and then also we have the Laplacian coordinates of the mesh itself. And we do the exact same thing over here. We have T0, which is our mesh, and we break that into T0 smooth and T0 Laplacian. All right. So if we wanted to get back the original mesh, well, how do we do that? And again, we're kind of reviewing this, but just to make sure, this is a mesh you can look at. This is a smooth mesh. This is a mesh that you can't look at it. It's a whole bunch of little teeny vectors, right? It's a little offsets. And so to look at this, it would just be a cloud of little vectors. So how do you get back to your original mesh? Well, you use that fact that if we had the Laplacian of the original mesh, we could get back to it. So what we actually store is S sub t hat is equal to then minus. So when I'm doing, I did a little terminology kind of thing. So these are the Laplacian coordinates of the vertex of this guy, and the Laplacian coordinates of the smooth version of this. So the thing that we're actually storing, and wave my hands a little bit out here, is this. The subtraction of the Laplacian coordinates of the original mesh. So we go through the original mesh, we take the Laplace operator, and we create a big long list of Laplacian coordinates, and that's that thing. Then we take the smooth mesh. Remember, I just created this using a filtered operation. Smooth, 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 smooth. And then I run this through the Laplacian operator and get that. And what I'm actually storing is the difference between the two. Still, can't look at it. It's just differences between Laplacian operators, and it's just a whole bunch of little teeny vectors representing the details. But you can kind of think about it. You say this is the difference between the Laplacian of this mesh, the Laplacian coordinate representation of this mesh, and the Laplacian coordinate representation of the smooth mesh. All right, why would you do that? It seems so weird. Well, no, it isn't, because we want to be able to get back to this. We're going to bend the smooth mesh, and we're going to apply the details. So if we wanted to get back to the original one, what do? We say S sub t, the source that at a certain frame is equal to the inverse Laplacian. Remember, that's not just a matrix, that's an actual operator, and they do that with a parentheses here. And they say take the Laplacian of the smooth mesh at whatever frame you're at, add in the details, and you can get back to the original mesh. Now remember, we know this. We have this source mesh. We've captured this. We want to transfer that onto that. So we're taking the Laplacian of the smooth mesh, and then the thing we stored, which was actually the difference between the original mesh and the source mesh, or the smooth mesh is Laplacian. Add those two together, and this gives us the Laplacian of the original mesh, right? Smooth plus, remember this thing was actually this smooth mesh minus that. So since this is that minus that, I can now take this and that, which are exactly the same thing. This is the Laplacian of the smooth mesh. That's the Laplacian coordinates of the smooth mesh. They cancel out. You get the Laplacian of the original mesh back. You do an inverse Laplace transform, you get the original mesh back. We are happy. We're so happy with this. All right. So now, next step, you say, all right, but this still bugs me. I want to make sure that I can, you see, the main thing is I have this for my source mesh. But I always want to keep where I'm going in here. The question is, I don't know what this should look like. Now I've got a frowny, nosy dog, and so on. I want to get these guys. So nose, smiling face, and happy, like that kind of thing. These are the guys I want to get, but I don't have those. So can we take this and make it a little bit better? So indeed, what we're going to do is go -1. Okay, that's the Laplacian that's going to take us. This, easy peasy, that's the thing. We can always compute that because that's the smooth mesh. And then we're going to do something else. We're going to say that this, we're going to take this and do a dt equals st minus s0. So remember what we're doing here. Or I mean, think about what they're doing at this point. They're saying, okay, we've got these details, these wrinkles, the things that make this face actually look like a real face. We're going to take the neutral pose and figure out the details for the neutral pose. And then, for whatever frame we're on with the high resolution capture that we've done, we're going to figure out the details for that current pose. And then we're going to subtract the two to get how those details have changed. So if I use this, super easy math, we can change this thing into S0 plus dt. Which doesn't seem all that like, why are you doing this? The S0 just cancels out, you get the ST, why should you do this? But no, this is important stuff. Because this is how this thing is going to be changing, and that's what we kind of really want. So we're gonna see that show up throughout this entire thing. So this is our final representation of a face. We'll leave it dt to sort of say this. So we have the smooth mesh of the current frame that we're on, the details that were inside the original neutral pose, and how those details changed so that we got to the current pose that we're at. And then we're going to do the exact same thing over here. We're going to create a TT. This is the mesh we want, the mesh that we eventually want to get. L1 LT0 TT plus T0 and plus ET0. Okay. All right. So this is actually kind of cool because the only thing we have here is the original mesh, the mesh of the dog with all the details of the dog and stuff. And now you can kind of see how they are thinking about this. What we're going to do is this smooth mesh is how the gross motions of this human face that we've captured move. And we've got a sort of one-to-one correspondence between these. So we're going to use the gross motion of the human face to sort of drive the gross motion of the dog's face, or whatever character that we're driving. Then, we've broken this out a little bit. We've got the original details of the face of our human. And we've got the original details of the face of our dog, or the character that we're trying to drive. And now what we're trying to do is watch how those details of the human face change. And we're going to apply it, and I totally blew the subscripts on that. Sorry about that. So what we're going to do is say, I'm going to apply the change of the details of the human face, the change of the details of the dog's face. And what we're hoping to do is say, look, we're not going to apply the human's details. We don't want that. We don't want to know exactly how the human frowns. What we want is to make sure that the dog still looks like the dog. The wrinkles change the way the humans change. Which is a clever idea, right? You're not forcing, you're not stamping the wrinkles of this guy's face onto the dog, because that would be a little weird. What you want to do is watch how those wrinkles change and take the wrinkles that were already in the dog's face and change them similarly. You want to make sure that they behave in the same way. Because that's the whole goal. We don't want this thing here to look like this guy. We want to transfer the performance. And that's how things change. I'm digging this paper. This is a really cool paper. Okay, so far so good? We good? Looking at the audience as if I care. I care, really. All right, so last time, what do we do? I know we got this. I'm just going to erase all this. We'll bring it back if we need to. Okay, so blend shapes. We love the blend shapes, and we're going to represent this stuff with blend shapes. So blend shapes come into the picture. And we're going to have a blend shape representation of this guy. So S of T, the original mesh, oh, and this blend shapes only matter to the smooth stuff. So we're not going to try to really push our blend shapes to try to capture everything in the thing. We're just trying to come up with blend shapes that capture what is happening to the smooth version of the face. Equals, and B, and these guys are all vectors, but I can't use the vector thing because that means smooth. All the way to Bn W T. So this, if you break it up, let's look at this a little bit. This is a big matrix. Remember, at the end of S sub T over here, you can barely see that. And then end of S sub T, this is just vertex 0, vertex 1, vertex 2, vertex 3. And these are all smooth vertices, right? But that's the representation of the mesh at this point, all the way down to vertex, whatever, 2000, that represents our mesh. So what we're basically doing is saying, I want to have columns of this matrix where this is a basis 0 sub 1, basis 0 sub 2, basis 0 sub 3. And these guys are all vertices as well. This is just like the neutral pose of this face. And then this might be the pose of the face where it's smiling. 1 sub 2, B, 1 sub 3. That's, my indexing is a little wrong and so on. And so there's just pose after pose that are represented in a column format, which is just the length, the vertices all just stacked on top of each other. And then over here, we have a weight matrix. W, and this can be, 0, W1, W2, and so on. And you multiply this weight, and basically you're saying, think about what happens if you multiply this times the top row of that. You're multiplying B over W0 times this vertex, W1 times this vertex, and adding them all together. So this is W0 times B0, W1 times B1, W2 times B2, plus, plus, plus. And all those guys add up to be the first vertex. And the same weight applies to this. And the same weight applies, the weights all apply down here. So basically you're just saying, how much of this pose added to this pose, added to this pose, makes the pose that we're currently at. Easy blend shape review. So what we want, if we have this blend shape, we need to be able to figure out the blend shapes that represent our smooth poses. So these guys solve this problem, R min. We're going very fast here, WT, because we've already covered this last time, but and this is the set of all WTs, and this is the set of all base shapes. Sum of 1 over equals 1 to T of n, difference between our base shape matrix, B1 or B2, B3, times W sub T minus the actual pose that we're at, squared. So that's the length of that, with WT greater than or equal to 0. What? We're going through every pose in the source input animation. And we have the source mesh right here, right? And this thing, that little thing right here, is supposed to create the source mesh. So this is basically saying, let's figure out a B1, B2, and B3, and a set of W's that, and the W's notice change over time, the base fit shapes don't. That when you add them all up and you compare them with the shape that you actually want, you make this as small as possible. You minimize the error between what this gives you and what you want. All the while making sure that the weights are always greater than or equal to 0. You can't have negative weights. Negative weights screw things up. Now, this can be done. Surprisingly, this can actually be done because you think about it and you're like, wait a second, you wrote 1,000 vertices here, and then you have a whole bunch of base shapes. You know, how many base shapes do you have? Like 50. So that's 50,000 different numbers times 3 that you have to solve for. And then on top of that, you're solving for all these weights that change every frame. Is this possible? Yeah, actually, yeah. There's some cool papers. There's a Huang et al. In 2011 did this, where you're basically extracting the base shapes out of this. And in fact, we've been exploring a lot of these things. There are greedy algorithms that do this. And the way they do it in this paper is they basically say, we're going to take B0 is equal to S0. We're going to take the first face and make that the base face. And then what we're going to do is start choosing from other shapes in here and checking. If I take B0 and say B17, oops, 17, and make a matrix out of that, and we can do that. We can just have B0 here and B17 here, and B17 is equal to S17. And then we have our weights. Can I create all the shapes that are in the performance? Well, actually, by adding B17, I might be able to do better than just what if I just use B0. Because B0 is going to be awful, right? It's going to be, you're going to say the entire performance is just the first shape, one after the other after the other. But if we start adding in B17 to the mix, well, maybe now we can get a little bit better. And if we do get better, we're going to keep it. This is going to be sort of a greedy algorithm. And then we'll start randomly choosing other, read the whole paper, and they have a technique of doing this, but you start choosing in other shapes and saying, what if I added on to this matrix, B52? Well, B52 plus these might actually make it worse. The solution to this, when you're looking for the weights, might actually be worse. So we throw that out. Or it might not make a big enough change in the error that we want to use it. And we'll look for another one. So there's an iterative way of taking shapes from the original performance and populating it through here to get this thing to get as small as you can. And all along the way, you actually solve for the weights, which is cool. So at the end of this, you get a certain number of weights. They eventually stop before there's an error threshold that it falls upon. All right? So at the end of this, you get rid of this. That's done. We have this. Right? We have that. We found it. At the same time, over here, we say, let's pretend prime, WT, So let's pretend that we have the exact same thing that we have over here. We can't, right? We don't have this. These guys, we don't have any performance of the dog. That's a big question mark. We do have this original shape. So the question is, can we somehow create something like this? Turns out we can. So this is where we kind of laughed last time. We're going to be talking, but then we got into more details, and we have enough time, I think, to go into this. So first of all, how do we create that? Well, there's this thing that we've talked about over and over again called deformation transfer. We've done this in multiple chalkboards. That is going to take this stuff and make that stuff. And by this stuff, I mean the base shapes and the weights. So, and in fact, we don't even really have to worry about the weights yet. What we're looking for is mostly the base shapes. So we formulate the transfer process in an optimization framework by adopting the deformation transfer method in Sumner and Popovich, 2004, to construct target-based frames, base shapes, from the source base shapes. Because people are extremely sensitive to mouth and eye movement in the facial animation, we also extend our optimization framework by incorporating the lines. And that's really where we stopped last time. So what we're going to do, and this is the equation, D smooth, and all this is working on smooth stuff, remember, prime F I B I prime T 0 or minus D smooth F I B I comma S 0 smooth. Oh my God, this equation. It's not all that hard. L, oops, I, L, smooth, E, I, comma T 0, D, I, L, smooth, I, S 0. Squared. Okay, wow. Unfortunately, they're using the letter D, and I mentioned this last time, twice. D previously was the difference between the Laplacian coordinates. This isn't that. This is the deformation operator. This is a deformation operator that says how, if I have a deformation representation of a triangle, each one of these little eyes is for a triangle, and we're doing this over the entire set of faces of the triangles. If I know how a triangle looks in the original shape, so this is how a triangle I in base shape, in the base shape that we're working on, so whichever base shape that we're working on, it is I. Let me make sure I get my indices correct. No, I take this back. This is I is the current base shape that we're working on. The D converts this into a whole bunch of big string of deformation representations of triangles. So D actually is going through the, take it back, the F is the face. That's the triangle that we're actually on. So we're still comparing all the faces. So we're looking to see how a certain triangle in our mesh, so we have our face, we have a triangle here, and we represent that triangle using the difference between the vertices and the first vertex of the triangle and the cross product of those two. And if you take those three vertices and turn them into a matrix, or those three vectors, so take that vector and that vector and that vector and put them in as a matrix form, that basically represents the state of that triangle at that frame. If we're in a different pose here, and that triangle has changed shape, this is going to produce a different matrix, where there's a vector here, and a vector here. So that triangle has deformed, right? This is the rest shape of that triangle, because this is the smooth version of the neutral face. And this is the rest shape of that triangle in the smooth version of our target face. So this, remember, is our dog. And we're basically looking to see how much has this thing changed, right? We reconstruct the facial basis function of the target model by minimizing the following objective function, where the first term ensures that the 3D geometric deformation of the source model is consistent with the deformation of the triangle model. And I have lied to you a little bit. Hold on. Sorry, I'm going really fast. So this is looking how the triangle on this shape has deformed from the source shape. So I made a mistake where I was going between models and that just didn't seem right to me. So this is saying, here's a representation of our neutral pose. So this is S0 and the smooth version of that. Then we have a representation of our base shape. Let's say this is base shape 7. And remember, it's a smooth version of the face because we pulled it out of there. And so this might be him frowning. And that triangle is deformed. This thing takes the two matrices of this, multiplies them together to represent sort of how that triangle has deformed. You basically use these vectors here to create a matrix. You use the same vectors here to create the matrix. And then you multiply, we call this one, well, let's call this one E sub S0, and this is E sub E17. If you take those two matrices, you then go E sub E17 times E sub S0 inverse. You multiply those two together, and that is the result of that. When you look at it, you go, all right, and look at deformation transfer in order for this. But what this basically does is it's a characterization, a matrix characterization of how the neutral poses triangle deforms into the space shape. And we do the exact same thing with our target model. We say, hey, I've got the neutral pose of the dog, and I'm looking for a base shape of the dog that should be frowning. Right? So this should be a frowning dog. And the triangle should change similarly. So the thing is, this is a really cool thing about this whole process, is that you aren't looking at match this triangle with this triangle. That doesn't work. What you're looking for is match how this triangle changed, deformed to get into that. So you're basically taking out the triangle's exact shape. This could be a big triangle, a small triangle, or whatever, and reducing it down into the sort of, well, vectors of triangle, vectors that change shape a little bit here. So now this triangle doesn't have to look anything like this guy, but we want to make sure that when we create this base shape for this dog, that the deformation of that triangle is actually similar to what we got in our original page, or the original source data. So the dog will still look like a dog, but the deformation that gets this dog shape into this frowny dog shape will be very similar to the deformation that took our human into a frowny human shape. That's pretty cool. And you can actually do this. You can actually solve for this stuff. There's an optimized via linear system that they talk about in the Sumner Popovich paper. And you can actually do this kind of thing. The thing they added onto this, just like last time, was that we can also do this with the lines. So, oops, I've already written it down. That's the triangles. These are the lines around the eyes and the mouth. So they actually draw lines that represent this and say, hey, I want the outline of this mouth and the eyes to move similarly. So it's just another layer of this, and they come up with a way of creating the deformation matrices for that. And Jeff Wettig, who wasn't here today, I don't think he is, figured it out. So we can go into some of the details. If you want some details for that, I understand that a little bit better. Okay. So now this is really where we start. So what do we have? We have the source mesh represented, smooth source mesh represented by a set of base shapes and weight. We have now just created the base shapes for our target mesh. Don't have this weighting thing though. Well, actually we kind of do. The optimization with the linear system, with the reconstructed target base shapes and the weight vectors of the source sequence, we can reconstruct the smooth target mesh in each frame by a weighted combination of target face bases. So once we do this, think about what we've done. We have the base shapes of the source and the base shapes of the target, the dog. And we have whatever frame we're at. So we can then sort of say, all right, given that we have the base shapes of this and the base shapes of that, can we figure out the weighting that changed in order to produce this face and figure out the appropriate weighting on this guy? Well, yeah, we can actually. In fact, they almost should be the same. They should be very close to each other. But not quite. All right. Now, this is the fun bit. But that's just the smooth stuff. This has basically made this smooth version of our actor look like a smooth version of our dog. We want all these details. This is where we get back to the Laplacian. Right? So now, I say, all right, let's think about this. We're going to try to figure out a way to apply the details back in there. But like I said, remember, we don't necessarily want to transfer the exact details. We want to transfer how they change. So there's another argument. Don't be afraid of that. That's just a fancy way of saying something is scary. BI prime. WI prime. Okay. So, first of all, we want to do this transfer. And we want to find the base shapes and the weights that will produce the animation that we're looking for. But we also want to give the user control. So in this section, we discuss how to extend the facial transfer method to allow the user to edit and control the retargeting of the facial animation. So I misspoke. We haven't quite got to the details. We'll come to that in just a moment. But we're basically going to give the user a little bit of control. So we developed an efficient optimization algorithm that computes both the face bases and the weight vectors based on a couple of things. First of all, this term is the deformation transfer error of all the target face bases. So this is the thing I was just talking about. That's that great big B prime squared plus B. So L, or this is faces, this is lines. That's that great big thing that we were just talking about. But there's more. The second term ensures that the temporal behavior of the target expression sequence is consistent with that of the source expression sequence. So this is one of the cool things about this, is that not only are we looking at a single frame when we're trying to figure out, what the pose of this character should be with or given this pose, what the dog should look like. But not only that, this thing says, I want this to be smooth through time. And when I'm saying smooth, I don't really mean smooth. I mean that it should change the same through time. So the way EW is EW, this is basically the energy, right? of this is t equals ts plus tw. There's some time window here. Release that. You guys know what that is. So this is saying, okay, I know my weights for the source matrix, right? Or source mesh. And this, again, smooth source mesh. I figured those out due to fanciness that I did before. The D operator is basically saying, how is this weight changing per frame? So the D operator is horribly simple. It's basically saying, let's take weight t plus 1 minus weight t and produce a vector saying that the weight of this thing, and remember this is a big weight, so it's a weird ass vector, but it's a multi-dimensional vector. But it's basically saying, how is this weight changing from our current frame to the next frame? And what we want to do is make sure that the weights I solve for my dog are changing in a similar fashion. So that if my eyebrow goes up really fast from one frame to the next, I want to make sure that that happens on the dog. I don't want the dog to lag or do anything like that. I want the temporal behavior to look the same, which is kind of cool. A lot of times we only work on one frame at a time. This is saying, no, 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 you can't. You actually have to have a window where you want to make sure that, and notice it's a window, it's not the entire thing, so this thing can actually travel. We want to make sure that things behave similarly. And in fact, this window can also be used to apply edits. So we can actually say, I want to make this eyebrow move up a little bit faster. I want to change it. And if I do that, I want to make sure that it blends well with the rest of the animation. And this thing can do that. It's kind of cool. All right, so the second term ensures that the temporal behavior of the target expression sequence is consistent with that of the source expression sequence. In our implementation, we minimize the weight gradients of the source and target models. These are the weight gradients, how they're changing, in a user-specified temporal window, resulting in the following objective function. All right? And finally, this one, E sub T, measures how well the retargeted facial performance matches the user-specified constraints. So this is where we can actually specify a constraint to this mesh. We can select points. We can say, I want to make sure that the chin, or a blob of this chin, goes a little bit farther down, because when my actor opens his mouth, the dog is not, the mouth isn't opening correctly. So I'm going to edit this. I'm going to actually change this. Wow, this is the cool power of this. Instead of changing the weights, remember, we're solving for the weights. We're not moving this. What we're actually doing is creating the blend shapes. We're solving for both the blend shapes and the weights. That make sure that the motion transfers correctly and also supports any edits that we do on a particular frame. So their whole idea here is my actors move their mouth, open their mouth up wide. The dog's face doesn't look good when that happens. So I'm going to change how the dog's face looks on that one frame. I am going to make sure that those constraints are satisfied. I'm going to make sure that those constraints also fit in temporally with the rest of the animation so that it doesn't look like a huge pop. And I'm also going to make sure that the blend shapes behave correctly given that original framework. And when I do this, I'm actually going to change the blend shapes themselves. So by changing one frame, I'm going to affect the entire sequence. So that if my actor opens his mouth wide in multiple points on here, by changing that one frame, it should actually affect everything because I've changed the blend shapes that I'm actually using to generate the performance of that dog. So anytime we go back to that pose, those blend shapes will kick in. Bob's your uncle. And so this is horribly silly. It's super easy. It's E equals the sum over time window. This is a time window element TP P sub t, this is the edit, and then the sum over all the vertices involved, P sub b prime comma t prime. And all you're doing is looking at how far away. So you're basically summing over a certain period of time and a certain amount of the whatever points have been edited. And we're looking to see where my target vertex is compared to where I want it to go. This is where the user is specifying how far I want it to go. And this basically says, I want you to go where the user specified you to go. You have a weighting schema in here, so that can be a sort of soft blend. You can have the user, doesn't have to be hard constraint. But you can say, by changing these parameters in front of each one of these weights, you can say, I really, really want this thing to follow where the user specifies, or I really, really want this to be smooth, even though the user you can play a little bit around with how closely you follow the user. Oh. They also add one other extra energy thing where they compare the length of edges in some areas, but we'll skip over that. This is actually a crazy optimization, but you can solve for it using a non-negative linear solver in James and Twig 2005. And it's an iterative kind of thing. They solve for the blends, the blend shapes, then they solve for the weights, and then they go back and adjust the blend shapes and the weights, and they do it over and over again. But it evidently works. And this thing doesn't run that slow. This thing is running in about 15 seconds for a sequence. So this isn't horrible. This is 2014 paper, I think. So reasonable. All right, finally, we've got 3 minutes. We can finish this paper off. Sorry, yeah. 3 minutes. Finally, the details. The details are actually relatively simple to do. There's this thing called, in one of the papers, there's a Sorkin paper, 2004. It's one of those surface mesh optimization papers or something. They talk about transfer of detail using surface coding. And it's actually not that hard. The whole idea is, with the Laplacian reconstruction, the Laplacian reconstruction doesn't work under rotation. If I have a mesh, a face, and I convert it into a weird-ass Laplacian representation, so here's all my vectors, and there's all the details of that. And I convert it back. I said that you had to specify some constraints in order to convert it back. Typically what you do is you take a single vertex and you pin it in world space, and that gives you enough information to reconstruct the surface that you started with. But if you took multiple vertices and pinned them in world space, still works, comes up with a nice solution. If you translate those multiple vertices, and I actually move them over here, and I do the inverse Laplacian, no problem. It'll create the face, but it'll create the face over there. If I take these vertices and turn them, all of a sudden things go to hell. The Laplacian is not good with rotations. It'll create a weird-ass looking version of your face. There are ways of dealing with this, though, and that's one of the things with the surface coding. It actually says, if we do this, if we figure out how each mesh, or each triangle in the mesh rotates, we can basically create this thing. So here we go, we get a new d sub t prime equals, this is for each vertex. Rotation of a single vertex, now they use this different terminology, eta v minus, I'm horrible at writing that letter. 0. For each v in S. S T We transfer the fine-scale motion d Laplacian coordinates of the source model to the target model by rotating the Laplacian difference of each vertex on the source mesh computed with the rotation RV. The cool thing is, in some papers, figuring out what RV is a bit of a chore. In this paper, figuring out RV is not all that big of a deal because we have the smooth version of our mesh that we just solved. And so RV can be computed for how a mesh here rotated compared to the mesh here, or the face here rotated compared to the face that's over here rotated. So this rotation basically says, I'm going to take our Laplacian coding and do the rotation appropriately to make this thing work. The last step, we reconstruct the target mesh from the fine scale motions of this and then plop it back onto our target. Now remember, this eta thing is how the Laplacian coordinates change from the source mesh to the thing. And so this is basically saying, all right, we're going to rotate this so that it fits accordingly with the target thing. And we'll apply that into this when we finally reconstruct the original target. By doing that, remember, it's the Laplacian of the target smooth plus, target t plus smooth target plus b t prime. Yeah, that's t. This thing will, when we do that, will give us back the t, the mesh that we're looking for. So I wrote this down very rapidly. What is this? This is Laplacian of the smooth target mesh at the current frame. Do we have that? Why, yes, we do. We have that because we just solved for it. Remember, we solved for all those base shapes and the weights, so we can actually compute the score. So we can compute the Laplacian of it. Do we have the Laplacian coordinates of the original source mesh? Yes, that was easy. We have the source mesh. Do we have the dt prime Laplacian coordinates? Why, yes, we do. We just took the Laplacian coordinates of our source mesh, which is this thing, and rotated them so that they fit onto here. So we basically turned the source mesh's Laplacian coordinates into this. All of a sudden, we solved that with our neat little Laplacian inverse operator, where we have to constrain at least one of the vertices here. Boom. We just created a dog's face that moves like the human face. Awesome. The cool thing, one other cool thing, because we've totally run out of time, is that with this, it's that simple. But if you modify this, you can enhance or decrease the details that you're pushing in here. So they then spend the next page of this paper talking about how scaling the change in the Laplacians, the coordinates, will actually apply deeper details, or you can edit this with this. And they build up another framework of doing that. It's not nearly as sexy as the other framework that they did for the smooth stuff, but it works. It seems to work pretty cool. And that's all there is. And that's it. Literally, the results, they were very happy with the results with an 8K resolution, 80,000 vertices in a mesh, a sequence length of 360 frames, the number of bases being 10. They computed it in a minute. With more bases, like one guy to a dog, was 80,000 mesh or vertices in a mesh, sequence length of 1,300 frames, 28 bases, 2.9 minutes. That is not bad. There's some sick ass computations going on in here, and they're doing all of this 1,300 frames in 2.9 minutes. That is really not bad. So props to this paper. Cool things that they did. First of all, figuring out the base shapes that incorporate edits. This stuff, applying the Laplacian coordinate stuff, the details onto it, by monitoring how the details change from the neutral pose to the current frame, is a very cool concept as well. And I don't know, there's a lot of neat things in this paper. I'm impressed with this. This is an old, very large paper, and there are some cool concepts in here. Next week, there's where we got I'm really looking to do a paper on real-time facial capture by cow. It was a 2000. It was 3 years ago. 3 years ago. How many years ago? 3 years ago. 2014. Yeah. Either that or I have been promising to get back to Theano, and I'm almost there in terms of examples. We'll maybe do a Theano. One or the other. If not Theano next week, Theano that week after that. Questions? Oh my God. No questions. We're done. I have to hang up.
Thank you.
Does that make sense?